Just 1 second. I'm not able to see this. Yeah. Not this one. Sorry. Yes. I'm just trying to see where the full screen is there. Okay. Is it visible now to everybody?
Yes, yes, it is. Yeah, it is.
Okay, yeah.
Okay. Dr. Mishra is reader F at NISER Bhubaneswar. So he is also a visiting faculty at TCG West, Kolkata. He is also associated with ICTS TIFR Bangalore. And his primary research interests include quantum simulation, quantum phase transitions in strongly correlated system, and topological phase transition and circuit theory. So, Professor Mishra, Dr. Mishra will be talking about novel physics from quantum walk of interaction bosons. So, yeah, please go ahead.
Okay, thank you very much for this introduction. And I would like to thank the organizers for presenting our recent works in this interesting month-long conference, which have attracted many people, especially students. I heard from Professor Paningai that students are getting really interested in this meeting. Okay, so today I'll be talking about something related to quantum walk of interacting bosons, and I'll show you in various contexts that how novel physics can emerge from quantum walk. So first of all, before I move on to the topics, I would like to mention that this is a conference on quantum information and quantum technology. And the term quantum walk is very well related to quantum technologies, because people have realized that quantum walk can be used in various different contexts of quantum technologies and quantum communication, quantum search algorithms, quantum computing, and so on. But in this talk, I'll be talking mostly on the applications of quantum walk to study fundamental physics. So although this quantum walk is known to be very useful for quantum technologies, its usefulness in understanding fundamental physics is very important. And the term interacting bosons is added here because we are going to see how quantum walk of few particle dynamics or the dynamics of few particle state can reveal something new about some subsignatures of many particle dynamics or many body initial state. And at some point, this quantum walk of few particle system also reveal novel scenarios. Okay, so studying the dynamics of many interacting particles or a true many body system is always challenging, both theoretically and experimentally. And therefore, this type of dynamical systems or dynamical problems involving few particles, although they are interacting, can be very easy. And this can provide a type of a bottom-up approach to your many-body dynamics. So therefore, the motivation is to study the dynamics or quench dynamics or the quantum walk of interacting particles. So in this context, we consider interacting bosons, because the motivation comes from the rapid progress in the field of ultracold bosons in optical lattices. And this is one of the very important and very powerful tool or simulator to perform various different studies based on many body physics, quantum phase transitions, etc. And this has been the topic of interest in the last 2 decades, starting from the first experiments by the group of Emmanuel Bloch to study or to observe superfluid to Mott insulator transitions. So optical lattices are the lattices or the artificial lattices made up of counter propagating lasers, which can trap ultracold bosons into them. And when the bosons are trapped in these optical lattices, they experience this periodic potentials of this ledgers created by these ledgers. And this mimics a setup which is similar to your electrons in periodic potentials. And they can provide useful insights about various different theoretical predictions which cannot be observed in conventional condensed matter systems. Okay, so this is a cartoon picture of optical lattice. You can see that these are the periodic potentials created by superimposing lasers, and the blue dots are cold boson, ultra-cold bosons. And one can create lattices of various geometries starting from 1D to higher dimension. And the fundamental model that describes this system is the Bose-Hubbard model, and this is very well known to people now. And this is a very simple and straightforward model which has two different terms. One is this kinetic energy of bosons hopping between the nearest neighbor sites. And this second term is the interaction between two particles, two bosons sitting on a single site. So this is kinetic and the interaction terms. And this is the first motivation. And the second motivation is this, which is called the quantum random walks. And in this paper, they have shown, they have extended the classical random walk in the context of quantum physics, where they introduce the concept of quantum random walk and show that due to the quantum interference effects, the average path length can be much larger than the maximum allowed path in the corresponding classical random walk. So this is a very important statement. In the classical random walk, your random walk is confined to the initial position. I mean, we have already studied this. But in the case of quantum regime, quantum particles, due to this interference effects, they can have an extended regime of propagation. And this gives us an extra mileage over the classical random systems. So if you look at this slide where we have compared the classical random walk with respect to this quantum random walk, here you can see this walker is starting from this initial position. After a long time evolution, you can see this roams around the initial position. However, in the quantum case, this quantum walker has finite probability to spread to the left or to the right. So therefore, at equal after a certain interval of time, it can cover the entire space or entire lattice sites. So this is very important. And one can see from the spreading of this random walker in both classical and quantum cases. Here you can see the classical walker has a maximum probability near to the initial position after a long time evolution, whereas the quantum particle has spread to a very large space in the lattice, on the lattice. So this is very important, and as I said, this importance can be understood in the context of quantum technologies. But here, in our case, we are interested in one of the type of quantum walk, which is called continuous time quantum walk. And in our case, this continuous time quantum walk is very convenient because one can have access to any value of the time, as compared to the other form of random quantum walk that is called discrete time quantum walk, which takes place in a discrete time space. But here the time can take any value, it can vary continuously. So that is also important. And then the Hamiltonian is time independent. So this is a very simple problem which can be coined as this unitary time evolution of an initial state. So this is the final or most important equation, which we have already studied in our quantum mechanics books. So this H is time independent. So this psi 0 is an initial state. And after a time evolution, we get this psi t. So basically, what we are doing is we are quenching some of the parameters of the Hamiltonian. It's a sudden quenching of some Hamiltonian parameter. Then we study the time evolution of this state. Okay, so one can call it as a quench dynamics, or in terms of random walk, people call it as a quantum walk. Okay, so here you can see that this is the initial particle. This is the initial state where the walker is sitting here. It has some kinetic energy J to the right and also to the left. So therefore, after a time evolution, you can see this wave packet or the wave front of this wave function of this particle has spread to the entire lattice site, which can be seen here. Okay, so here this is the experimental observation in cold atoms in optical lattice setup. Here, this is the optical lattice where this particle is a single particle or single boson is trapped here. And this equation, this quantity gives you the probability of spreading of the particle. And this is the local on-site particle density. This is the left side is a theoretical prediction of a quantum walker sitting here at the initial position, then how it spreads over the lattice sites. And this is the experimental observation in the group of Marcus Greiner in Harvard. And here you can see this one-to-one correspondence between theory and experiment. Okay, so this is a very important observation. And after this, also, or maybe during in the last 1.5 decades, you can see that there are several observations of this quantum dynamics of single particle or quantum walk of single particle has been done in various artificial systems, including trapped ions, photonic lattices, waveguides, superconducting qubits, and also people have predicted some kind of quantum walk in the photosynthetic excitations in biological systems. Okay, so this is all the story about a single particle quantum walk. There is no interaction. This is just a tight binding model. It's a single particle problem. Now, if you introduce interaction, then the effects are very interesting. The effect of strong correlation. If you have more than one type of particle, then effect of statistics can come into picture. So these things becomes very interesting. So novel quantum effect may emerge from the interplay between wave nature, quantum statistics, and interaction in the many-body system. Okay, so therefore people have studied two particle dynamics or two particles quantum walk, and there have been several experiments, pair of cold atoms in optical lattices, correlated photons in coupled waveguides. So these are like more than one single particle quantum walk. So microwave photons in superconducting circuit. So I mean, recent experiments showed how more than one particle can lead to various interesting phenomena. And this is a very famous paper by Andrew Child, where the theoretical proposal is also given for an universal quantum computer with interacting particles based on these Bose-Hubbard systems. Okay, so the key ingredient in all these observations or the theoretical predictions are bosons in periodic potential, because bosons are easily accessible in these kind of artificial systems. Okay, so correlated photons, cold atoms, these are cold bosons, microwave photons, these are all bosons. So therefore, the interest is, the focus is towards bosonic systems, which can be easily accessed in these artificial systems. Okay, so now just to highlight or just to build the foundation, let us try to understand the quantum walk of two interacting bosons in one dimension. Okay, so now we can have a possible initial state, which is something like this. The bosons are created at the 0th site. Two bosons are sitting on top of each other. So therefore, this is the initial state. And then we can have two different scenarios in terms of these interactions. If we fix J to be, say, the unit of energy, which is equal to 1, then U can be small, U can be very large. So if you perform this kind of dynamics, then what do you expect? So we expect an independent particle quantum walk, because in the regime of small interaction, these particles, they can behave like free particles. And one expects a single particle quantum walk or independent particle quantum walk. And if it is independent particle quantum walk, then the propagation has to be faster, because there is no interaction. They just move like free particles. It's a fast propagation. And if we look at the correlation matrix like this, then we expect diagonal as well as off diagonal correlation, because the particle has spread to the entire site. So if you compute the correlations between different sites, that this is kind of a density correlation, then you expect finite correlation matrix elements throughout the correlation matrix. However, if we have a very strong interaction, then the effective two particle quantum walk can be observed, because now the particles will start to interact, they talk to each other. Then we expect a slow propagation, and the reason for this will be given in the later slides. We would see slow propagation and only dominant diagonal correlation. And the reason for this is in the next slide. So here you can see this theoretical prediction or theoretical data for this two particle propagation. So here when U equal to 0, which is very, there is no interaction, then you can see even if the two particles are starting their quantum walk at the central site, here this is red, this is the density plotted here, and you can see that density equal to 2, which is the color bar on the right. This is two particles, they are sitting here. and they are spreading very fast and reaching the boundary quickly. And when this interaction U is strong compared to the hopping, then you can see that they are not spreading very fast. They are staying close to the initial position after a long time also. Okay, so here is the experimental observation by the group of Marcus Greiner, and for weak interaction you can see this probability or the correlation matrix element is finite throughout the grid. However, when U is strong compared to the hopping, then you see only the diagonal elements are finite. That means the particle remain close to the initial position. So this is the experimental observation using cold atoms in optical lattices, and this is the theory prediction. Okay, now what is the reason behind this two particles they are staying close to each other, or why they are forming a kind of bound pair? Actually, I mean, when they are initiating their quantum walk from here, they remain on top of each other. They don't split apart in the regime of strong interaction. So what happens here is that when the interaction is very small, in the case of weak interaction, you see that the entire band is of scattering states, so that means one can have easy spreading of the particles. But the moment you have strong interaction, then this band splits apart from this scattering band, and you get this isolated bound state band, or in principle you can call it as an anti-bound state pair, because the interaction is repulsive here. In the case of attractive interaction, this band may go down, go below this scattering band. You call it a bound state band, but here, since the interaction is repulsive, we call it a repulsive or anti-bound state band. And in the literature, this is called repulsively bound pair. Okay, and this physics behind this is that when these two particles are sitting on top of each other and the interaction is very strong, if you ask them to break apart, then they won't break, because if they break apart, this extra energy that will be released from this breaking has to be converted to this kinetic energy. And since the kinetic energy is very small compared to this, due to energy of resonant condition, this pair will not break. So therefore, these two particles will rather prefer to move together in the lattice, and this dynamics, so this is seen as a slow dynamics in the quantum walk. And here is the experimental observation of this repulsively bound pair formation. You can see that when the interaction is 0, and this A0 is this S wave scattering length, that defines this interaction in the Bose-Hubbard model or in the system of ultracold atoms in optical lattices. When there is no interaction, this normalized pair number vanishes or decreases fast with respect to time. But the interaction is when the interaction is very strong, so this remains finite after a long time. Okay, so this indicates that the repulsively bound pair is formed when interaction is very strong, and the two particles or two bosons are initially located at the central site or one of the sites. Okay, now the second possibility is if you have two bosons, two identical bosons, another possibility could be A0 dagger, A1 dagger acting on the vacuum, and that means these two bosons are occupying the two nearest neighbor sites. Okay, so in this case, what happens? I mean, we have already probably in this conference, people have already understood, or maybe you have heard about this Hanbury-Brown and twist type interference effects of photons. When these bosons are identical and they are not interacting with each other, then they will exhibit Hanbury-Brown and twist type interference. And the moment they are interacting, they start to interact with each other, then they cannot exhibit this HPT type interference. Okay, so here you can see that when interaction is small, the interference pattern is very, of course it is 0.7. If you make it 0, then this entire grid correlation matrix will be finite. But in the regime of weak interaction also, you see some finite interference throughout. Okay, and mostly the diagonal terms are dominant. You can see the main diagonal terms are dominant. But when this interaction is very strong, then these bosons, cannot form HBT interference, and they show some finite elements in the opposite directions of the main diagonal. And this is the experiment, and this is the theory data for this model when the initial state is here. And you can see here as a comparison, I have shown, I mean, I forgot to put the reference here. This is a paper by Jakob Zakrzewski, a PRA rapid communication paper. So here is the initial, one of the initial state when the two particles are created at the central site, and this is another initial state when they are on the nearest neighbor sites. So in this case, as you increase this interaction, you can see this pair formation is happening. That means you are seeing only the diagonal, main diagonal elements finite, and for very large, very strong interaction, only a single dot is appearing in the correlation matrix. That means this particle, they remain at the central site as a pair, bound state. But when they are starting from the nearest neighbor site, you can see a clear HBT interference when interaction is 0. And as the interaction increases, this interference vanishes, and you see that two points on the opposite direction of the main diagonal, they become finite. And this is for a very strong interaction. And if you compare this with the fermionic interference pattern or fermionic correlation, they are similar. So this gives us an idea that when bosons are next to each other and the interaction becomes very strong, due to fermionization, they don't form a bound state. I mean, unlike here, when they are on top of each other, they form a bound state due to interaction. But when they are next to each other, they cannot form a bound state, okay, due to the strong on-site interaction. Okay, so another possibility that I had shown this in the last version of this QIQT conference in 2022, I showed that if you have another state where two bosons are created on top of an uniform background of bosons, and then this Hamiltonian will become the Bose-Hubbard model, and this another term which is called a three-body interaction, because in some situation we have three particles sitting on top of each other, then the interaction will be something like this. So these are complex many-body problems. There is no exact solution. So exploration of this quantum work can be done using numerical methods such as time-evolved block decimation method or matrix product states. Okay, so in this regime, if we consider repulsive on-site interaction and attractive attractive three-body interactions, then we see interesting features where this is W equal to 0.5 of U, which is very small. W is very small and attractive, so minus 0.5 of U. Then you see that it's a very slow propagation, which is an indication of a bound state formation. And as W increases further and further, there is a faster spreading of this and becomes faster and very fast when W equal to U. And then as W becomes more and more stronger, then this spreading becomes slower again. And at the other end, you see another slower profile that indicates another bound state. So what does this exhibit? This shows that a slow propagation to fast propagation and then to a slow propagation as a function of this W. And we have fixed our U at 10 and J is the hopping, which is at 0.2. And U is fixed and W is only varying unidirectionally. That means it is only increasing. But from the profile, you can see that the slow to fast and fast to slow. So this is a very interesting scenario of reentrant dynamics. Okay, I mean, slow spreading becomes fast and then slow, although W is just increasing. So this can be also seen from this correlation matrix. Here you can see this is a clear signature of pair formation, then faster dynamics, then again localized dynamics. And this is a reentrant dynamics in the quantum walk of two bosonic defects on top of an uniform insulating background. Okay, and this reentrant dynamics occurs due to the resonance condition, because you can see that when W equal to U equal to W is negative of U, but they are equal of strength, then they cancel each other. The two on-site interactions, they cancel each other. So therefore the particles they don't feel any interaction in the system, so therefore they spread apart like a free particle. But as the interaction increases, the bound state again forms. So this reentrant dynamics requires two competing interactions. So what exactly happens here? In the absence of any W, these two particles, the extra particles, due to the strong on-site interaction U, they form a bound state that I had just explained here in this case. Okay, when the two particles are created on top of each other, they form bound states. That is what is happening here. Although there is a background present here, this background is uniform. So therefore these two particles, they don't see this, I mean, they feel that this uniform background is like an empty lattice. okay, because wherever they go, they feel the same interaction from the background. So therefore, the situation is same as A0 dagger on 0, okay, acting on vacuum. Okay, so when the two particles are created on this and the W is finite, so these two bound particles can move on the lattice freely. And then you see this when W is finite, so these two particles also form a bound state because your interaction W is negative, and instead of forming a trimer or three particle bound state, they prefer to form a two particle bound state, because if they form a three particle bound state, their hopping will not be, I mean, their effective mass will increase and effective hopping will also decrease. So therefore, to minimize the energy of the system, they rather prefer to form a two particle bound state. So these are the two extreme conditions. One case is W equal to 0, the other case is W is large. In both the cases, these two particles, they will prefer to form a bound state rather than a three particle bound state. Okay, so this is another example where we showed a reentrant dynamics. Now you can clearly see from here, it's a reentrant dynamics as a function of interaction, as a function of two interactions, as two competing interactions. Okay. Okay, now the story is now up to this point, the story is about identical bosons. Now what happens if we have distinguishable bosons? Okay, so far we have considered identical bosons. Now let us see what happens if you have distinguishable bosons and study the quantum walk. Okay, so the simplest case is two particles of different types, and I have given this arrow mark spin notations to distinguish the two particles, and you can consider this as pseudo spins. And this could be two different types of bosons, two different atomic species, or maybe two hyperfine states of the single species. Okay, and this is one of the initial state where the two particles are created at the same site, and these are at the nearest neighbor sites. And the Hamiltonian for this case is different, which is very similar to our Hubbard model of different spins. J sigma, this is J up and down, sigma is up and down, and this is the interaction between the species, on-site interaction, and this U sigma is the interaction among the individual species, for example, up and down interaction. Okay, and here we have introduced another quantity called hopping imbalance. So this is the kinetic energy imbalance between the two components, which is defined as delta equal to J down by J up. And again, we perform the same quantum work as prescribed before. And in this case, we can have two different types of correlation. This is the correlation matrix between the two particles, that is n down and n up, the density correlator, and this is for the same species. So this is A up dagger, A up dagger, A down up, A down up. Sorry, AJ down, AI down. Okay. So now you see, I mean, what we expect and what we see here for this initial state. If we have hopping imbalance or the mass imbalance in the between the particles, then you see that when interaction is 0, the heavy particle has a slower spreading. You can see a profile which is very slow here, and there is a very fast spreading, that is for the lighter particle quantum walk. And as you increase the interaction, this U is between U is the interaction between the particles. So since we are considering one particle from each species, then this interaction vanishes, because when n is 1, then this term is 0. So therefore this quantity, this term is not there in the Hamiltonian, because we are considering one particles from each species. So only surviving term is U up down, and we term this as U because up down is not necessary right now. We cannot distinguish between these two. I mean, there is no meaning of writing up and down. So we just write this as U. So this is the same U, that is the interaction between the two particles. So when U becomes stronger and very large, U equals to 10, you can see that this overall spreading becomes very slow. Okay, so that means these two particles have formed a bound state here. Okay, the same physics that we see for the indistinguishable identical particles, here also we see this. However, when they are on the nearest neighbor sites, we see something different. When U equals to 0, the heavier particle has a slower propagation, lighter particle has a faster propagation. As the interaction increases, Because of intercomponent repulsion, which is very strong, this lighter particle cannot penetrate through this heavier particles dynamics. So therefore, it has a unidirectional spreading compared to this. Okay, here they don't form any bound state. Only they spread individually. The heavier particle is spreading like this. It is not disturbed at all by the lighter one. So the lighter one cannot penetrate through the heavier one. And so therefore, this spreading is only happening on this side of the lattice. Okay, so there are several other analyses on these models. You can find more details in this article. I'm just showing it, showing some part of this work. Now, so in this case, we studied only the dynamics of two particles, one up and one down. Now, if you consider more than one particle here, so it's a 3-particle quantum walk. Okay, so 2 up spin or the 2 up particles and 1 down particles. So then the initial state is something like this. Initial state is A0 dagger square up and A1 down dagger. So that means I am creating one down particle here and two up particles here. Okay. So again, this Hamiltonian is same as before. And since we have 2 up particles present, so we can have U up finite here, and U down is 0. I mean, 0 meaning it doesn't have any meaning, but for convenience, we call U up and U down as U. And we define delta, again the imbalance, the hopping ratio delta, and we introduce some hopping imbalance by making delta not equal to 1. And in this case, we consider the interaction between 2 identical spins or the particles as 10. And our numerical simulations are based on this matrix product states, open source matrix product state. You can actually find this in the internet. It's a very nice library to study dynamical evolution of quantum state. And in the simulation, we consider the length of the system as 41 sites, which is quite sufficient to study the physics of this kind of model. Okay, so here also you can notice that there are 2 competing interactions, U up down and U sigma. So therefore, as expected from the previous case, one can have a reentrant dynamics in the system, because as I said, when you have 2 competing interactions in this case, there can be a energy resonance condition like this when U equal to W, and therefore this leads to some kind of reentrant dynamics. One goes from here to there. Similarly, here I have 2 competing interactions, U up down and U up or U down. So therefore, we expect a reentrant dynamics. So let's see what we see here. So this is the density evolution again, and this is since we have 2 different species, so therefore the density is summed over the species index sigma, and we plot NIT here. I mean, this is the time evolution of NI for different interactions. Now you can see that when U up down is 0, that means there is no interspecies interaction. Then the spreading is very slow. Okay. As the interaction becomes larger, the interspecies interaction becomes larger, then you see that there is something happening here, and then you get back to your original position. Okay, whatever was there before at small interaction, then you are also seeing this in the strong interaction regime as well. So this is a clear reentrant dynamics: slow, fast, and then slow. Okay, and this is happening in the limit because of another resonant condition, because you can see that U up down is just 10, and we have considered U to be 10. So intraspecies and interspecies interactions are same here, and before this point and after this point, the profiles are similar. So this is again a reentrant dynamics. However, apart from this reentrant dynamics, we see something very interesting, which is this. If I zoom into this resonant condition case, okay, now you can see here that we started from, look at this point, this is T equal to 0. This one is dark meaning the density is 2, so that means 2 particles are sitting here, and this is a bit red, which is equal to 1. So that means 2 1, the initial state is 2 particles on the left side. So this is the initial state, 2 particles on the left side, 1 particle on the right. So now as soon as the time evolution starts, you can see that the right side becomes completely dark. That means the density here is 2, and on the left it is all red. Okay, so what happens here? So immediately after a short time evolution, the right side which was having density 1 becomes 2, and the left side is something. I mean, there is a nice spreading of particles, unidirectional spreading of particle on this side of the lattice. Okay, and this density is 2, that means a pair is being formed. So this indicates that the pair which was here, we get another pair here on the right side of the lattice. Okay, and this is what up pair breaks, and one of them forms a bound state with the down particle. So what happens here is, this is the up pair. Because of strong on-site interaction of this up pair, they form a bound state. And as time evolves, due to this resonance condition, because U up down is also 10, then this pair breaks, and when this wave front or wave packet of these two pairs superimpose with this wave packet of this, then this blue and red, they form a bound state. So that is what is seen here in this zoomed in picture. This pair breaks and immediately another pair is created. The isolated up particle which was initially here, I mean there were two, one of the up goes here, and the remaining one up particle cannot penetrate through the pair, I mean it cannot penetrate through this massive object now, and therefore it will perform a quantum walk which is identical to a single particle quantum walk, and this has an unidirectional quantum walk like this. Okay, so here the local bound state of bosons due to only on-site interaction is formed. So as I mentioned, if you remember, I mentioned that the two bosons, when they start their quantum walk from identical, nearest neighbor sites, if you look at this, two identical bosons, when they start their quantum walk starting from this nearest neighbor sites, they cannot form bound state. Whereas when they are starting from the on-site, a particular site, then they form bound state. Here they cannot form bound state due to on-site interaction. But the interesting fact here is that if the bosons are not identical or they are distinguishable by some means, then although they have only on-site interaction, they form a on-site bound state. So on-site bound state, so in summary, the bound state formation of identical boson due to on-site interaction is prohibited because of fermionization. But if you make the bosons distinguishable, then on-site bound pair can be formed due to on-site interactions. Okay, so this is something very novel which comes out of this interacting system, interacting quantum walk. Here you can see this the signature of pair formation from this correlation. This is the up-down correlation, and the central dark spot indicates that there is a bound state, is up-down bound state is formed. However, for the up particle, which is now spreading as an individual particle, this has some interference pattern, although in one side of the lattice because of the unidirectional hopping, unidirectional propagation. Okay, so you can also clearly see this signature from the individual particle propagation. This is the up particle propagation, initially slow and then unidirectional, then slow, and the down one is having very slow dynamics throughout because they form, it's a heavy particle, and also the down and up particle pair is formed here, and also clearly a reentrant signature because this feature is on the other side. So reentrant dynamics is seen, and also a clear signature of pair formation. Now, to quantify this pair formation, one can compute this probability of pair formation, P up down, which is defined by this, and P up up. So now we want to see which pair is formed and which pair is broken. So now we have considered two different cases. One is delta equal to 1. That means there is no hopping imbalance. The two bosons have the same hopping. And you can see here that this is the dashed lines here. There is a red dash line, there is a blue dash line, and the red one is for up down and blue is for up up. So you can see this, that when delta equal to 1, as U up down increases, as the interaction increases, initially the up up pair is formed, okay, because up up interaction is large, and gradually this up up pair will break, and at some point this up down pair formation will probability will increase, and then at the resonance point, that means U up down equal to 10, after that they will break. I mean, again the up pair formation will be finite, and then up down pair formation will go down to 0. So this is a nice signature of reentrant dynamics. Sorry, reentrant dynamics. And interestingly, if this density imbalance is sufficiently small, delta is 0.02, now you can clearly see that the solid lines with boxes, the P up completely vanishes, and at the same point P up down probability is maximum. Okay, so due to this density imbalance, this pair formation or intercomponent pair formation is very large and at the same resonance condition. And we can also see this in the time evolution of these probabilities. This is the P up down and P up plotted as a function of time. And initially P up was finite because both the particles, up particles, were sitting on top of each other. Then as soon as the evolution starts, this up falls down rapidly and becomes 0. And at the same time, this up down pair probability increases sharply and then saturate. Okay, so this indicates that there is a pair formation, and this is again the dependence of P up down on the imbalance is plotted here. So you can see that when delta equals to 1, that is the equal hopping for both the cases, you can see that the imbalance is finite, but it is actually small compared to sorry, the P up down is finite, but it is small compared to the other cases when the imbalance is very large. That means delta is 0.2. So you can see that it increases and saturates as the imbalance increases. Okay, so what happens here is the following. So you have two up particles on one side, one down particle at the other side, and as time goes on, this up pair breaks and you get this up down pair. Okay, and this particle remains as an independent particle and it performs an independent particle quantum walk. So why does this happen? In the limit of equal hopping for both the components, and when the inter and intra component interactions are equal of strength or of equal strength, the energies of up pair and the up down pairs are equal. Okay, so therefore this initial state up at the 0th site and down at the first site, and up at 0th site and up down at the first site are degenerate states. Okay, so when this note that I'm talking about equal hopping strengths. When J up and J down are same, so these two states are equal. These two states are degenerate. Hence, the probability of finding both this and this pair are finite. So you can clearly see here when delta equal to 1, at this point, both these pairs have equal probability at the center. But as soon as you make this hopping imbalance, or you create a J up, J down small compared to J up, the formation of up down state is more favorable because the effective energy of the up down pair is up down pair favors to minimize the energy of the entire system. Okay, so therefore when there is an hopping imbalance, the up down pair is more favorable in the system compared to the up pair. So one of the state, this state is more favored when hopping imbalance is introduced. So that is the reason why we see that the up down probability is increasing sharply at this resonance condition when delta is 0.2. Okay, so the details of this finding can be seen from here. So where we have considered another initial state where we have performed 4 particle quantum walk. So note that as the number of particles in the system increases, the dynamics or the computation becomes harder and harder. But here we consider only 4 particles, 2 from the up particles, 2 from the down. And in this case, another interesting scenario happens. You get a trimer instead of doublet up down pair. You get a trimer of 3 particles. That means 2 down and 1 up. So this this pair breaks apart, and one of them comes here and forms a bound state of 3 particles, and this happens at U up down equal to 5. So one can energetically also see that in the case of this 1 up and 2 down, the resonance condition is U up down equal to 5. And here from this figure, you can see that initially both are 2 2 at t equal to 0, and immediately the right side becomes 3, and the extra one particle, remaining one particle, performs unidirectional quantum work like this. Okay, so it's a 3 particle bound state on the right and single particle quantum work on the left. So to quantify this, we compute up down, up pair probability, and sorry, this is a mistake. This is actually down down probability, p down down. Here you can see that at u up down equals to 5, these up down and down down probabilities are finite, whereas up probability vanishes, which is because of this. The up pair formation is gone to 0, whereas the other two are finite. Okay. We also see another resonant condition at 10, which is not very significant. The most significant contribution comes from here. Okay. So this is another important findings where we showed that 3 particle bound state can also be formed if the particles are distinguishable, if the bosons are distinguishable. Okay. Now, up to this point, I have shown that in all the cases, you need 2 competing interactions to see this reentrant dynamics. As I showed in this case, we saw reentrant dynamics, slow spreading to fast and then slow as a function of interaction. While we vary this interaction, we have another interaction there in the picture, that is this one. Okay, so 2 competing interactions, when they match with each other, that's a resonance condition. Because of that, we see some reentrant features. Okay. However, if we consider a simpler system, this is another interesting model called interacting flux ladder or Harper-Hofstadter ladder, and this is very widely studied in recent years, both in theory and experiment, because of the experimental realization of such systems using cold atoms in optical lattices, and also I think in superconducting circuits. So this model has been widely studied at the single particle level, and for the interacting system, for the many particle system, numerical studies and analytical studies have been performed using approximate methods. But the dynamics of this system, where you have 2 different legs coupled to each other, and particles are interacting, and this ladder is subjected to some magnetic field. Okay, so this is like your model of electrons in magnetic field on a lattice. So there you see this Hofstadter spectra and all these things. So here, in cold atomic setups, these models can be easily achieved by using bosons. Bosons are neutral, but you can actually create synthetic magnetic field for bosons by using the technique of laser assisted or Raman assisted tunneling. And experimentally, the single particle physics like this Meissner physics and vortex physics have been observed. But if you have interacting system, then the study of many body dynamics of this kind of setup is difficult. So therefore, recently some studies have been performed, at least one experiment by again Marcus Greiner, where they studied this interacting 2 particle quantum work on this kind of flux ladders. Okay, so the model is this: you have on-site interaction and this hopping between hopping among the legs. So P is A, B, that means this is A leg and this is B leg. So 2 types of hopping here, for leg A and leg B, and this is interaction in 2 different legs, so UA and UB. So interaction on this leg, interaction on this leg, and K is this rung hopping, which is associated to this phase called Peierls phase, and this comes due to this insertion of artificial gauge field or magnetic field. And this phase is defined by this: A is the vector potential and phi is pi by pi 0, and phi 0 is your flux quantum. And the quantum work is studied here by considering the following initial state, which is A0 dagger A, A0 dagger B. So that means we have created 1 particle on the 8th leg and 1 particle on B leg at the central rung. Okay. So in this case, we have considered J equal to 1, that is leg hopping equal to 1, and rung hopping equals to 3. And this is the parameter considered in the experiment I am mentioning about by the group of Marcus Greiner. And they have studied the chiral dynamics, because this kind of model exhibits chiral motion of the particles. One particle will move along the right direction in the upper leg, the other particle will move in the left side in the lower leg because of the magnetic field. And if the magnetic field is very strong, then one can see these vortex patterns in this plaquettes. Okay, so in this case, what we have done is we have considered the physics as a function of strong interaction, or sorry, function of interaction as well as flux strength. In our calculation, we have considered 25 rungs, which is around 50 lattice sites in the system. So what we have observed, what we have seen here is the following. So when U is weak, so this means the upper panel, I have forgotten to mention the strength. So the upper panel is U equals to 2 or 4. I think it's a small or weak interaction. You can see that as phi changes or phi increases, you see a faster moving faster spreading particle dynamics to slower spreading particle dynamics. So it's a monotonous change, a monotonous decrease in the profile in the quantum walk, fast to slow. Okay, but if your U is very strong, so here it is U equals to 20. So the lower panel is very strong interaction. So you see a non-monotonous behavior. So fairly slow, then fast, then slow again, slow, and then faster. So here, of course, I mean, it's not easy to see this non-monotonous behavior, but if you compare this with the upper panel, you can see that there is a clear decrease in the speed of the propagation, but here it is not. Okay, but this quantity of density is, I mean, it doesn't give you a clear signature from here, but to understand this more clearly, we compute the radial distance, that means the radius of propagation, radius of expansion of this wave function. Then if you plot this for U equals to 0, you can see that there is a monotonous change. So this is for U phi equal to 0, this is a fast dynamics. You can see that this is spreading faster, and as flux increases, the spreading slowly decreases monotonously. For phi equal to 25.25, this is small, 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 and small. For maximum flux, it is smaller. But if you go to the other side, when U equals to 20, then you see this non-monotonous behavior. When phi equals to 0, you are somewhere here, this one. And then phi increases, this rapidly increases to this, then decreases, and then 0.75, that's the smallest, the slowest propagation, then increases. You see, I mean, from here it goes up, goes down, then goes up. So there is a nice non-monotonous behavior in the dynamics. To quantify this further, we plot the slope of this radius of expansion at some point in this curve, and then you see this here. Okay, so this is the radial velocity plotted as a function of phi here. For phi, U equals to 0, you can see that there is a monotonous decrease in velocity, and for a strong interaction U equals to 20, it goes up, the velocity goes up, goes down, and goes up again. And this is something very interesting feature of reentrant dynamics, and here there is no energy resonant condition. So there is no competing interactions present in the system, and this is only happening when only one type of interaction is there and the flux is changing. And this, in other words, if you look at this profile, you also see another reentrant behavior as a function of U. So you can clearly see when phi equals to 0, there is a monotonous decrease in the velocity, but for phi larger, you see there is a reentrant. It first decreases and increases. Okay, so there is no need of any competing interaction as in the previous cases. Okay, so to understand this, one can look at the single particle band here, and you can see that when U equals to 0, then the particles, they behave like single particles, and as the flux increases in this case, you see that the band becomes flatter and flatter. So this one is for 0 flux, and gradually when flux increases, so phi increases, you see the band is flattening out, and therefore the dynamics become slower. Okay, so therefore this is becoming faster to slow. But to understand what happens at strong interaction, we first try to understand what is happening at 0 phi case. So here also we see that this is the velocity is decreasing from this black to this magenta. And what is happening here? We tried to plot the band diagram here, energy band diagram, and you can see that in the limit of U equals to 0, there are two scattering bands appearing. here, and therefore the speed is maximum. But as you increase this on-site interaction and make it large, then you see that this scattering band shrinks and another bound state band appears here. And because of this bound state band, this dynamic is becoming slower in this case. And this is the case for u equal 20. I'm right here. I mean, I'm along the y-axis, and this is the slow case, which is here. And you can see that from the correlation matrix, this is the free particle dynamics. Therefore, we have a nice correlation matrix here where all the elements are finite. But here, when u is very large, because of this bound state formation, you can see some bound state nearest neighbor type bound state signature, which is actually a wrong pair localization. I mean, the two particles which are located initially on the rungs, they form a wrong pair state. So therefore, you see a slow dynamics in the system. As we vary this flux, for this case u equals to 20, this wrong pair actually start to break due to this phi, and therefore the speed increases. And once this wrong pair is completely broken, then the particles, they try to, this phi would try to suppress the velocity. So therefore, as the phi increases, this particles velocity decreases again. And when this phi becomes very strong, then that means the magnetic field, the artificial magnetic field becomes very strong. So at this case, at this point, these particles actually form the vortex state. Okay, so they come very close to each other. Instead of, when the when the field strength is very weak, they stay on the legs. But when the field strength is very strong, they come close to each other. They form these vortex states. So therefore, they again try to stay on the leg, on the rungs. Therefore, the formation of wrong pair becomes prominent again. So you can see from this correlation matrix, if you look at this and this, these are signatures of slow spreading. This is also a signature of slow spreading. So slow becomes fast, then slow, and then slow, although it is slow, but it is faster than this. Okay, so you see this is, there is a nice non-monotonous signature. Slow spreading becomes fast, slow, then fast. Okay.
Dr. Mishra, we have 3 minutes or 5 minutes.
Yeah, no, I'm done actually, and this is the last, probably the last. Okay. So the more details of this can be found from here. So what I have shown so far, the summary, I would like to mention that in all these cases, I mentioned that to see this reentrant dynamics, usually in the many particle system, getting a reentrant feature in the dynamics is not very usual. Okay, so it's unusual. But we showed in different cases that if you have two different competing interactions, then one can see this reentrant dynamics due to resonance condition. But here in this case, this particular case, although there are no competing interactions, only one type of on-site interaction is there, but this flux can introduce a reentrant dynamics in the system. And this reentrant dynamics is robust. It goes up, comes down, and then again go up. Okay, so that is the new finding in this recent work, which is, you can see this in arXiv. And of course, I showed this non-trivial physics of bound state formation of two distinguishable bosons. So this is the summary. Two identical bosons at nearest neighbor sites don't form on-site bound pairs due to strong on-site interactions. If the bosons are distinguishable, then they form on-site bound pairs. So this is the main message. If the bosons are distinguishable, then only they can form on-site bound pairs. And we also showed reentrant dynamics of two competing interactions, reentrant dynamics if two competing interactions are present. And in the case of flux ladder, the reentrant dynamics is possible due to competition between interaction and flux. There are some typos. Sorry for that. And thank you very much for your attention. So all these things can be found in these papers. Okay, so any questions?
Okay, thank you very much for this beautiful talk. So floor is open for the question. So
yeah, Tapan, I have a question, small question.
Yeah. Yes, sir. Yes, sir. Yes.
That this bound state due to repulsion reminds one of high TC materials.
Yeah.
Of course, that is for fermions, isn't it?
Yes.
So what is the basic physics behind the bound state behind the
Yeah, so this is the physics actually. So if you, so for example, this one, if you see this first picture here, where the cross is put, red cross. So now my two particles are sitting on top of each other. Now, and the U is very strong. It's very large and repulsive compared to the hopping. So now if I ask this particle to be broken, if I say that, okay, this particle should split apart, then this interaction has to be released. The energy has to be released and it has to go somewhere in the system. So since there is a very strong off resonant condition, and this energy cannot be utilized as kinetic energy in the system, so therefore this pair cannot break. Okay, and instead this pair will try to move together due to some effective hopping. Therefore, you see this bound pair formation. But if you solve this two particle problem, yeah, you see this isolated bound state band which is sitting up in the spectrum.
Yeah. Got it. Thanks.
Any other question?
I have questions.
Yeah, please.
Yeah. Thank you for your talk.
Thank you.
Let me. In your, you are using term interacting photons. So, do you mean interference of wave functions of photons?
No, I'm just talking about bosons because I'm talking about strongly interacting bosons. So if I talk about photons, then achieving this strong interaction or strong non-linearity is difficult. So yeah, so I'm just talking about bosons. So it could be atoms or microwave photons or anything. But by some means one can introduce very strong interaction or strong non-linearity in the system, then one can see this interference between the wave functions of these particles.
Okay. In one of your slides, distinguished photons, two competing interactions, three photons or bosons are created. So in this case, energy is not conserved. So three photons are created and nothing annihilated. So are you considering non-conservative interaction?
No. I'm just creating an initial state where my initial state is just with two particles, two up particles and two down particles. All these are bosons. Okay, so I have distinguished these bosons by putting this arrow mark, up arrow and down arrow. And this could be in the experiment. I don't know how to make photons distinguishable. I mean, if we can have two different types of photons with some polarization. But the easiest case to think about this is, say, you have some atomic species, bosonic atoms, and the blue ones are like particular type of atom. The red one is another type of atom. Okay, so you can create this kind of initial state in the experiment where you can create an optical lattice and load this two component condensate in this system, and selectively you can lower the two sides potential and then make them very deep, and then remove all the other particles from the system. Then you can create this initial state. So that is what was my idea.
Okay, so maybe last question. Could you please share benefits of using quantum walks? Because in quantum optics, one can use space portrait by using Wigner function and can see quasi distribution of X and P. In your case, what are the benefits one can see?
Okay, so I was actually mentioning in the first slide when I started that this quantum walk has several benefits in the context of quantum search and quantum technologies and quantum computation. But here our motivation is to use this to study the dynamical evolution of a few particle initial state, to understand the physics, to address the many-body dynamics, or in certain cases, we expect new or novel phenomenon. That is what I mentioned here. I mean, you don't see this non-trivial bound state formation or reentrant dynamics if you consider a pure many-body state. And this is a feature of only this few particle dynamics. So this is the motivation behind this, to predict new phases or novel phases And if somebody or someone can see this useful in some other context, then it will be, I mean, very interesting. But at this point, I mean, we don't think, I mean, within our expertise, I don't see any application, a real life application of this kind of predictions. But up to this point, it's all on fundamental studies.
Thank you.
Yeah, I have one quick question. So, Dr. Mishra, what is the resonance condition in this case? Maybe I missed.
Yeah, this is a resonance condition. So this is the intraspecies interaction, which is 10J. Okay, and when this you see this, when up down is 10, so same energy.
Okay.
Up and up down are all same.
Okay.
That's the resonance condition.
Okay, so we are running out of time. So thank you very much for this beautiful talk. So okay.
Yeah.
So the last